let's start now. So last time we proved Carstan's theorem, namely that if K is a field in which Q is dense, then every closed subgroup of a Lie group over K is a Lie group over K. The condition that Q is dense in K is important. So the field is either QP or R. Those are the only cases which will work. Okay, now I am going to use that theorem to deduce.
Where exactly did you use that Q is dense in this field?
Well, where exactly did I use that? The point is that, at some point, for example, in the case when it's a periodic field, I looked at x pen x, and n varies over integers, and the closure is x per zpx, and that's a zp is an open subgroup of qp. That kind of thing is true only for qp. The closure of z will not be open in general field. So that's one of the places where it's used. I don't know, maybe it's used again somewhere, but I'm not sure. Something like that. Okay. Anyway, I showed you an example. Namely, you take complex numbers, that's a Lie group over C, and real numbers are closed subgroup, and it is not a complex subgroup, complex Lie subgroup. So that you can manufacture, again, take some finite extension of QP, say, and then take QP itself. That won't be a subgroup over the bigger field. Okay, that's the kind of example. Okay, now I also introduced the notion of a representation, rho G2 GLN K group homomorphism. Representation is a representation, an analytic homomorphism, analytic group homomorphism. Who is the representation? It's a linear representation. I may not want to say GL and K, I may simply say GLV, where V is an n-dimensional vector space. We want it to be an analytic homomorphism, but let me point out one fact which I forgot to mention last time. If you like, it's a proposition. Suppose f G to H is a continuous homomorphism. Of Lie groups for K, again Q dense in K, then F is automatically analytic. This is a consequence of the closed subgroup of a Lie group being a Lie group in the case of these such fields. So let me give you a proof of this. It goes like this. You take, you have this continuous form from G to H, and look at G cross H. This contains the graph of F, set of pairs GH, G cross H, which H equals FG. It's obviously a closed subgroup. The graph of a continuous function is always closed, so it's a closed subgroup. Hence, a Lie group, it's a Lie subgroup. Over K, of course, and that is because our Q is dense in K. That's Cartan's theorem. Okay, now look at this. We have the following situation: gamma f is contained in G cross H, and your projection of G cross H on G as well as on H. So you get a map like this, gamma f to G. This is the one-to-one map because it's a graph of a function. This map gamma f to G is one-to-one because if GH is identity, then G is H is FG after all. So follows that if once G is identity, GH is also right, the pair GH also becomes identity. So gamma f is one-to-one. Now gamma f is an analytic submanifold of G cross H. That's what we know by Cartan's theorem. It's an analytic submanifold, and therefore, if I look at this map is analytic and the projection is analytic, so this map is also analytic. It's a 1-1 analytic map. I want to conclude it's an analytic diffeomorphism. If I do that, then clearly the map from G to H can be described as G to the graph to H. And once I know this is analytic, the composite is all going to be analytic. So it's enough to prove that this 1-1 map, analytic map, has also inverse is analytic. How do I prove that the inverse is analytic? To prove that the inverse is analytic, it's enough to prove that the differential map at every point is an isomorphism. Because we already know it's 1-1. Once I know its differential map is isomorphism, locally it's analytic, but being analytic is a local property. So the inverse will become analytic everywhere. So the only thing to prove is that the Jacobian map, differential map, is an isomorphism. Now here I make use of a theorem which I do not know if you have seen this. Sarge's theorem. It says the following: if, in fact, I probably don't have to use Sarge's theorem. I can use, in fact, I can use inverse function theorem. Like, let me put it like this. Where on earth is the test? One way is to use the Sarge's theorem, but I don't think it's really necessary. Okay, the point is that notice that this is a group homomorphism. If rank at the identity is not the maximal rank, everywhere it's the same rank. So it's of lower rank. And if you have mapping of an analytic manifold into another, which is of lower rank than the maximum possible, then both are the same dimension, then it necessarily goes into a smaller subset. It cannot be onto. So your map U M of analytic manifolds of constant rank R less than dimension n cannot be surjective. Well, this follows from some version of the inverse function theorem or the implicit function theorem, if you like, because you take a small portion of this manifold, look at the image, the rank is constant. So if you take a sufficiently small portion, the image will be a strictly lower dimensional manifold. And then this gamma f is a countable union of such compact neighborhoods, compact sets which map onto lower dimensional manifolds. Lower dimensional manifolds are nowhere dense, so the union has to be nowhere dense, so the union cannot be surjective. So gamma f to G cannot be surjective. That gives you a contradiction. So this implies gamma f to G has maximal rank, which implies in turn that gamma f to G is an analytic isomorphism, analytic diffeomorphism. And f itself, so if I call this mapping, let me give some mapping name lambda, then you see, and this is P2, the second Cartesian projection. Notice that f equals P2 composed with lambda inverse. These are both analytic, is analytic. So every continuous, now all this is done over K, and it's not true over other fields. For instance, complex numbers you can project to real numbers. That's a continuous map. It is real analytic but not complex analytic. Okay. So once again, if Q is dense in K, any continuous mapping is analytic. But in practice, what will happen is that this continuous mapping will be analytic over smaller field. You can think of a Lie group over K can also be thought of as a Lie group over QP. Because K contains QP, you can think of any K itself is a manifold of dimension n over QP and so on. So a Lie group over a field K can be thought of as a Lie group over a smaller field, and as such it will be analytic. And in many contexts you will be able to prove that the function is analytic even over the big field itself by using some supplementary information. Okay, now getting back to representations. So I can also think of this as simply a continuous homomorphism, because any continuous homomorphism is going to be analytic, except if I am working over K. If I am working over QP or R. If it's not such a field, you have to be a little more careful. But any continuous homomorphism comes close to being analytic in some sense. It's analytic over QP or R as the case may be, but may not be analytic over KR. Again, anyway. So let me now go back to talking about representations. So I am interested in I defined the adjoint representation last time, which is representation from G to GL of G, so which is the Lie algebra. Is the adjoint representation, and it induces, this is analytic over the whatever field you are working with. If K is the field, this is an analytic over K. Everything is an analytic homomorphism over K, and so it's a representation in this sense. And it induces D add, which is denoted small add, is the induced representation from TEG to TE of GLG. This of course is same as endomorphisms of G, and this is the Lie algebra of G, and so we get a mapping. This is called small add. And I told you yesterday that which I asked you to check out, add x on y is bracket xy for xy in G. The adjoint representation is the representation obtained in the following fashion. Recall, G acts on itself by inner conjugation, fixing the identity, and therefore it acts on the tangent space. The differential of the inner conjugation acts on the tangent space, and that is it, which has been identified with G, and that is the representation. Okay, add xy equals bracket xy, xy in G. So you have this nice representation add. So note one, let me also another fact which I forgot to mention earlier is the following, which is quite easy to prove. If GH are Lie groups and GTH is analytic homomorphism, what do you want to say? One moment, what did I? Suppose GTH is analytic homomorphism. Yeah, the thing I want to say is the following. And DF is the induced mapping of the Lie algebra of G, Lie G to Lie H. We'll also denote it by F dot if you like. Then exponential T F dot x equals f of exponential dx. The exponential map commutes with the homomorphism. This is more or less obvious because it's if you take x and how is the exponential map defined? You essentially take the one parameter group of x and they take the image, the one parameter group of x, the two have to be compared. And from that it's quite obvious that this is going to be true. The exponential commutes with analytic homomorphism. These are facts one has to know. And from this, it's also clear from this that as a corollary you find that exponential t add x equals add exponential dx. Special case. Well, I'm applying it or in the case of if I take rho to be the representation and if I denote rho dot the corresponding thing, you will get something like rho dot rho of x dx is same as rho dot of x t times rho dot x. For any more generally, rho representation, rho dot induced map in Lie algebra you find exponential t rho dot x equals rho of exponential dx. Of course, exponential tx is not defined for all t. Wherever it is defined, wherever both sides are defined, you can put in the equality. So these are facts which I'll be using, some of the facts. Okay, now with this background, I can now state the next theorem, which is the central theorem of Lie theory, which says the following. Let G be a Lie group. G is Lie algebra. And H a Lie subalgebra. Then there is a Lie subgroup H, I H to G, that is a Lie group H and an analytic homomorphism of H in G, which is injective and such that the differential map is also injective at every point, such that the differential of I at identity maps the Lie algebra of H, maps Lie H isomorphically onto H. So every time you have a Lie subalgebra, you have a subgroup, a Lie subgroup. That's what the assertion is. It's all over. If it's a Lie algebra over a field K and a subalgebra over the field K, the corresponding subgroup is also over K. As I said, I'm going to use Cartan's theorem to prove this. In most literature, you will find it the other way around. They first prove Cartan's Lie's theorem and then deduce Cartan's theorem at a point. Okay. How does this go? We have now the representations add, which goes from G to GL of G. I am going to define certain subgroups of this group G now. I will define G1 to be the subgroup G in G, such that add G stabilizes H, keeps H in itself. That's obviously, sorry? Huh?
No, in the statement of theorem, last line, on to.
Isomorphically onto H. Sorry. H is the subalgebra. That's right. Now, I define G1 to be the set of elements G in G, such that at G preserves H, keeps H in itself. It's obviously a closed condition. It's a closed subgroup. G1 is a closed subgroup. And is therefore hence a Lie group over Q closure in K a priori. But actually I want to claim it's a Lie group over capital K itself. It's not just the closure. And the reason for that is the following. The Lie algebra of G1 a priori over Q closure is precisely the set of elements X in G, X in the Lie algebra G, such that add X H is contained in H. I am treating G as the Lie group over Q bar, if you like, and then I claim that this is the Lie algebra. Why? If you take anything from the Lie algebra, if you take the exponential, that should fall into the group we are looking at. It should fall into G1. I take anything in this, any X in G such that add X H is in H, then look at add exponential. Let's look at exponential Tx and see what add of this does on H. I claim it's contained in H. Why? Because add X Tx, as I have already observed, same as add X T times add X. Add X is a endomorphism of the vector space, and I look at exponential of T add X. The same as this. Apply this to H. The same thing as applying this to H, but this is sigma T power n add X power n by n factorial applied to H. Add X keep H in itself, so all powers of add X also keep H in itself, so this whole thing keeps H in itself. So what you find is that add X T X H is contained in H. So you find that the Lie algebra of G1 as a Lie group over K or Q bar is this subspace set of X such that add X H is contained in H. But this linear space is actually space over K, linear space over K, it's stable under K. If add X preserves H, lambda times X, add of lambda times X also preserves H, because H is K linear subspace. So this is K linear, K Lie algebra, Lie subalgebra. And therefore, if I take the exponential of that, it gives you an analytic submanifold over K locally, and then by translation everywhere you find it's an analytic submanifold. So all this shows that G1 is an analytic submanifold. Okay. G1 is contained in G, and on the other hand G1 also contains, claim is G1 contains exponential Tx for all x T small and X in H. In other words, I want to say the Lie algebra of G1 contains H. That is clear because add X preserves H. Therefore, it's contained in the, see, say here. So the Lie algebra of G1 is all those things which preserve H, but H is stable in the bracket within itself because H is a subalgebra. So add X, H is contained in H for every X in H. And the Lie algebra of G1 is being described here. Lie algebra of G1 is here, therefore it obviously contains H. Okay, so H is contained in Lie G1. So in other words, I can replace G1 by I can replace G by G1. G is a Lie group, and I took a Lie subalgebra of the Lie algebra of G. Now G1 is a smaller group. It's closed. Its Lie algebra again contains H. If I can prove that in G1 it's a Lie subgroup, obviously it's a Lie subgroup in G also. So can assume that G equals G1. What's the advantage? Can assume the point is, if you look at the Lie algebra of G1, in the Lie algebra of G1, I don't know if I gave it a name. Let me call it Lie algebra of G1. Let me simply call it German G1. In H is contained G1. It's not mere subalgebra in G1. It's actually an ideal in G1. Ideal is the obvious definition. You take a subalgebra. It's an ideal if bracket xy is in the ideal for every x, the bigger algebra, and y in the subalgebra. It's an ideal. So H is an ideal in G1. That gains us something. You know, not just look at subalgebras, it gets an ideal. But I will cut it down even further. Let me denote by G2. Now, let me point out something here. The group G1 acts on G on its own Lie algebra by adjoint representation. And stabilizes H. Hence, it acts on G1 by H, the quotient space. If you have a group acting on a vector space and it stabilizes a subspace, you get a natural action on the quotient. If you like, in matrix terms, you have a big vector space on which the group operates, so you get a matrix group, and it lives in subspace. So if you choose the basis suitably, you will get 0 in the, you will get 2 blocks and 0 below the 2 blocks and something above the blocks. And then if you take the block on the left top corner, that gives you a representation on the quotient. It's all clear, it's analytic, because it's only part of the, all those functions come from as matrix entries in the original function. So you get an analytic representation on G1 by H. So get G1 to G1 by H. And let G2 be kernel of this homomorphism. It's G1 to GL of G1 by H. G2 is kernel of this homomorphism. Let's call this sigma, kernel of sigma. G is a homomorphism, analytic homomorphism of a group over K, of a Lie group over K into GL and K for some K, some n, and therefore the kernel is going to be a Lie group of the same kind. It's a Lie subgroup, it's a closed subgroup, and this is a Lie group over K. G2 is a Lie group over K. And G2 again contains, Lie of G2 contains H. Contains H.
Are we assuming Q is dense in K?
Sorry?
Are we assuming that Q is dense in K?
No.
Are we assuming that Q is dense in K?
No, at this point, no.
Then how how do we conclude that?
No, it's a kernel of a homomorphism. If you have analytic homomorphism, the kernel is analytically grouped of the same kind, because it induces a mapping which is k-linear in the Lie algebras, and the kernel is the Lie algebra of the kernel is precisely the k vector space.
So, and how did you conclude that G1 is an analytic submanifold?
When I say analytic submanifold, it's over k.
No, G1.
G1 is also analytic submanifold over k.
How did we conclude?
I said that I look at the Lie algebra, and the Lie algebra is the Lie algebra over k. Okay, so the exponential image is going to be a submanifold of the, it's a k submanifold, because the exponential map at the identity is a diffeomorphism of a neighborhood, analytic diffeomorphism of a neighborhood onto the neighborhood of the identity in G. And the subalgebra G1 is something, it's the k analytic submanifold, so it maps into a k analytic submanifold. A vector subspace is a k analytic submanifold. So I now look at the kernel G2, which is a smaller group than G1. Can be, of course, the whole, but no, I look at this homomorphism, you get the kernel I call G2, and Lie G2 again contains H, because how does H operate? How does H operate in G1 by H? H takes all of G1 into H. So when I take add X with X in H, add X acts as 0 here, and therefore exponential T add X will act exponential T times 0. That's how it will operate, which is the identity. So the kernel, the Lie algebra of G2 contains H is the conclusion. So we have a situation when not only, now the point is this, not only is H an ideal, you find that so G2 H is completely contained in H. So H is not merely an ideal in G, H was an ideal in G1, but in G2 it's more than an ideal. It's not only an ideal, but it's an ideal which contains the bracket of G2, which is G2 which is in H. The commutator of G2 is in H. Not only is it an ideal, but the commutator of G2 itself falls into H. Why is this? Because add X operates on 0 and G1 by H means what? You take X in G1, Y in G1, the bracket should fall into H. So bracket X Y is in H. So G2, the commutator of G2 is inside H. That's the conclusion there. Okay. So we have a situation when we have replaced the group G first by G1 and now by G2, and the point is that, so we have the following situation, to reduce the problem to the following case. When G is such that G mod G bracket GG is abelian. Sorry, G mod H such that H is G such that H is an ideal in G, and G mod H is abelian. Bracket GG is in H. I'm also saying that G mod H is an abelian. Is abelian because bracket of two elements of G falls into H. So in the quotient, bracket of any two elements is 0. So it's an abelian Lie algebra. So we reduce a rather special situation from the. So for this, we would like to show that H is a Lie subgroup. In this situation, H corresponds to Lie subgroup. How do I do that? Now look at G mod H is abelian. It's a vector space. So pick a basis, say x1, x2, xp of G mod H, and set Gi equals sigma k xj j less than or equal to I. Sorry, and EI be this. This is G mod H. Sorry, EI. Yeah. This is the abelian Lie algebra. So every all brackets are 0. So EI is an ideal actually in G mod H. Everything in any subspace is an ideal there. And let me also denote by GI pi inverse of VI, where pi is the map from G to G mod H. Every pi inverse GI is a Lie algebra. And let me also set G naught equal to H. What I will now show is that inductively, by downward induction, starting with Gp minus 1, I will show that to Gp minus 1 there is a Lie subgroup. Then Gp minus 2 there is a Lie subgroup inside the group Gp corresponding group Gp minus 1 and so on. Finally, we will be ending up in the case where you have H contained in G1. Notice that every stage it's a codimension 1 situation. So we have reduced to proving the statement to the following case. Suffices to show the following. Let G be a Lie group and H inside G, which is Lie G, be an ideal of codimension 1, just one dimension less. Then there exists a Lie group H, a Lie subgroup H I H2 G as in the statement of the theorem. In other words, I have reduced the general problem to the case when you have a codimension 1 ideal. Instead of an arbitrary Lie subalgebra, I have reduced to the case of codimension 1 ideal in a Lie algebra, in the Lie algebra. Every step, each GI is of codimension 1 in GI plus 1. And the last one, GP, is the whole of G. What I call GP is the whole of G. GP minus 1 is of codimension 1 there. GP minus 2 is codimension GP minus 1. So construct the group corresponding to GP minus 1. Then you are landed in a Lie subalgebra of codimension 1 in GP minus 2. That gives you GP minus 2 and so on. It's a downward induction if you like. And you finally end up proving that it is. So it is enough to prove this statement. The whole problem is reduced to the case of a codimension 1 ideal rather than arbitrary Lie algebra, Lie subalgebra. And of course, at every stage you have to be a little careful. Make sure that you get a Lie group over K. But that's okay because each of these vector spaces are all, every stage the Lie algebra is defined over K. So codimension 1 case is the only case that is relevant. Now here, how do I handle this? I need a little theorem from about the differential forms, differential 1 forms, as you will see. So what is the situation? You have G and you have Lie algebra of G and a subspace H is an ideal of codimension 1. What does this do? You have the Lie algebra G, and from that you can have a map into G to G mod H, the natural map, which can be identified with K. In other words, you have a linear form on G, which gives to you a linear form on the tangent space at every point by, if you translate by, you get an invariant differential form, differential 1 form. That is, get a linear form omega G from the tangent space G to G2 K for every G in G, which is left translation invariant. In other words, we have an assignment of an element in the dual of the tangent space at every point. For every G, you have an element in the dual of the tangent space. You get such an assignment. Such a thing is called a differential one form. So you have a form omega. At identity, you call the form omega equal to omega e, which is the form from G to R. We also have the property that omega of bracket xy is 0 for every xy in G. Sorry?
That is K.
Oh yeah, K. Sorry. Omega of bracket xy is 0 for every. Such a form is what is called a closed form. If you have a form like this, the invariant form satisfying this condition omega bracket xy equals 0, it's called a closed form. And I don't know if you must have come across this business about in your MSc classes. A differential form they write is f dx plus g dy plus h dz. And then they talk of closed forms and exact forms. Right? This is a more general situation. I'm in an n-dimensional manifold. I can talk of forms and just now state what I want more carefully. So something about differential forms in general on manifolds, which I need as a background for this. So a differential M analytic manifold an analytic differential one form on M is an assignment of an element in Tm star, which is same thing as home Tmk for every M in M with the following property, such that in a coordinate chart UF omega, give it a name, analytic differential one form omega. Omega takes the form sigma I equal to 1 to n ai dxi, where ai are analytic functions. What do I mean by this? What is dxi? We have a, once you have a coordinate chart, you have a natural basis d by dx1, d by dxn, d by dxn of the tangent space. The dual basis is called dxi. dxi 1 less than or to I less than or to n is the dual basis to d by dx1 dx2 d by dxn. In other words, dxi on d by dxj is the Kronecker delta. Take the dual basis. Then at every point you can write omega at a certain point m is dxi at m multiplied by some coefficient depending on m, and then as I vary m, I get omega as a linear combination of the dxi with some coefficient functions. These functions have to be analytically defined, exactly as we did with vector fields. With vector fields, we wrote d by d, some ai d by dxi. I am writing ai dxi using the dual basis. That's all. Okay, that's what the analytic differential one form is. And a one form is said to be, let me, before that, a one form omega, analytic one form omega on M is closed if the following thing happens. omega x omega y minus y omega x minus omega bracket xy is 0 for every pair of vector fields. Omega evaluated y will give you a function. I can apply the differentiation with respect to the vector field x. X omega y is a function. Similarly, y omega x is a function. Bracket xy is the vector field, omega can be evaluated, that gives you a function. If this happens, you call the form closed. The condition of closeness can be described as follows. If you have the form a d by dxi, suppose, first of all, it requires a little bit of checking. A priori, you see this x omega y minus y omega x minus omega bracket xy seems to depend on the vector field and not just the vector at that point. However, you can see that if it's finally this expression, let me call it d omega, define d omega of xy as x omega y minus y omega x minus omega bracket xy. A priori, this seems to depend on the vector field, but you can show that this depends only on the value of x and y at a given point. Choose two vector fields, x prime and similarly y prime. Suppose they are the same value. The tangent vector at a certain point of x as well as x prime is the same, and similarly y and y prime is the same. Then this expression depends only on that value and not on the extended vector field. That is, what I want to say is this: d omega xy is also equal to d omega x prime y prime if at m. So at a point m, d omega xy is this expression. It seems to, what you get here is a function a priori. So at a point m, it makes sense, equals d omega xy at m if xm equal to xm prime and ym equal to ym prime. This is quite easy to prove. I'll say a few more words about this operation, which takes omega to d omega. D omega, see, omega is a one form. D omega gives a scalar for every pair of vectors. So it's called a two form. In fact, it has some other properties. It's an alternating two form. If you exchange x and y, it becomes its own negative, as you can see from the expression on the right hand side. It becomes its negative. So it's an alternating two form on the tangent space at every point. That's so from one form to two forms, you've got an operation called D. Anyway, so you can apply this to a form like omega equal to ai d by dxi. In particular, suppose I take x to be d by dxj and y to be d by dxk. What happens? D omega of xy is this expression. This is an expression which I want to be 0. X is d by dxi. So x is d by dxj. So it's d by dxj of omega on d by dxk. Omega on d by dxk is simply ak. So dxi by ak minus d by dxk of aj. The bracket of d by dx and d by dxj is 0, so this is 0. So if omega is closed, you necessarily get the condition dak by dxj minus dxk by daj equals 0 for every pair kj. Conversely, if this statement is true for every pair kj, you can easily check it's closed, because any vector field can be written as a linear combination with function coefficients of the d by dxj. Use that fact and you can easily prove that this is the condition of closed. Once you write down the local coordinates, the condition of omega being closed is this. Okay. And omega is said to be exact if there is a function f on m such that omega on x equals x on f. If xf equal to omega x, for every x, for every vector field x. Once again, it is enough to check this condition when x is the form d by dxi. Then you can take linear combinations and things will get out. When d by dxi, what does this mean? This means d by dxi of a, what I want to say is the following. To say something is exact is to say in a local chart the value on d by dxi is the partial derivative of a fixed function, and you find an exact form is closed because the value, the AIs will be AK will be d by dxk of a function, and AJ will be d by dxj of the same function. So it's a matter of saying the order of the partial differentiation does not matter. So exact implies close. And what is true is that lemma, if omega is a closed one form on M, for every point M in M, there exists a neighborhood V of M such that in V omega is exact. Every closed form is essentially exact, is what it is. That is, in other words, if you have a bunch of functions f1 f2 fn such that delta fi by delta xj is equal to delta fj by delta xi, then there is a phi such that all the fi's are partial derivatives of that phi. This is an easy exercise to prove, and you have probably come across it in the case of three variables. In the case of R3, three functions. You know, the point, what's happened is this: you take a function f, then from a function f, you have come across the way of getting a vector valued function called grad f, gradient of f. And then if you have a gradient of f, if you have a vector valued function, you can talk of its curl, okay? And you have the famous result that curl grad f is 0. This is a generalization of that in any number of variables. Grad f corresponds to taking partial derivatives all the variables, and taking curl is for every pair you attach something. In the case of three variables, there are only three pairs. So vector valued functions go to vector valued functions. Here, in the general n-dimensional case, if you start with an n-dimensional vector valued function, you will go into n minus 1 by 2 dimensional vector valued function because there are so many pairs of that. Okay. So, in fact, there's a more general setup. I'll talk about that a little later. Let's see. So the lemma says if omega is a closed one form on M, then there exists a neighborhood of V on N such that omega is exact. And it's not that this, that means omega equals df. This f is not unique because you can modify it by a constant. But that's about the only thing that can happen. If df equals dg, df f minus g is 0, which means all the partial derivatives are 0, which means f minus g is a constant. So f is unique up to a constant. And you can only make the statement locally, it is not true globally. The famous example is, if you like, if you look at take complex variables, take dz by z in the punctured disk. Okay. It is df log z, but log z is not well defined. It's a multi-valued function. You cannot do that. But locally, you can define logarithm. In a small portion, you can choose a single-valued logarithm, and there you can do it. So locally, it's true, but not in general globally true. What happens globally is it gets involved with the topology of the space you're working with, or the manifold. The punctured disk has a different topology from the disk itself. So in the disk, it's true that any close, if it's everywhere defined, look at dz by z, it's not defined at 0. It's defined only in the punctured disk. But if you take something which is defined on the whole disk, then it is, on the whole disk it will be all right. But if you take something in the punctured disk, you can't expect it to only locally it's okay. So topology plays a big role in talking about differential forms being exact and closed and so on. I'll say a few words more about that another 10 minutes later. Now, the point here is this. Once you have this lemma, what do you have here? This omega is a where is the form omega? Yeah. I have this form omega here. Okay. Omega of bracket xy is 0. We know that. But that is the same thing as saying this I claim implies that d omega xy is 0. To check that d omega xy is 0, it is enough to check for vector fields which at every point give a complete linearly independent set of a basis for the tangent space. It's enough to do that because then you can see everything becomes a linear combination of such vector fields with function coefficients, and then you can easily see that d is 0. So it's enough to check d omega xy is 0 for xy left invariant. It's enough to check this, but this is equal to x omega y minus y omega x minus omega bracket xy. We know that omega of bracket xy is 0. Omega x and omega y are constants because x is linear, x is invariant vector field, and so is omega is an invariant differential form. It takes the same value at all points. So omega y is killed by x, y omega x is also killed by x. Omega bracket xy is 0 because of this, so it is 0. So d omega is 0. Once d omega is 0, we know that omega is closed, which means it's locally exact. In other words, there is a neighborhood so going back here, there is a neighborhood u of 1, u of e in G, and the function f from u to k such that omega equals df. And you can also assume that f of 1 is 0. F of the identity element is 0. The one constant is at the value at one point is in our hands because you can modify it by any constant. So choose as an f. And the point is, we also have further properties for f. I claim that fxy equals fx plus fy if xy is sufficiently close to near identity. Why is this? Freeze y. Then what happens? df. You calculate df xy, freeze after freezing y, and after freezing y, this will disappear. Fy is y is not a variable any longer. Y is frozen. So df is what you will get. Here also you will get df because omega is equal to df, and I am translating omega by y. It doesn't change. The point here, one point to note here is that it does not matter. I could have frozen x or y, it does not matter, but because the particular differential form I have is actually invariant both on the right and left. Because g by bracket gg is abelian, so and the differential form lives in the quotient. It's 0 on bracket gg, lives on the quotient, and there you get an abelian group, and there left translation, right translation makes no difference. So the differential form you have is actually bi-invariant, both sides. So when I take df and translate by y, I get the same form. So because of this relationship holds. So it's more or less, it's like a homomorphism. F of 0 is 0 and fx, except that it's not defined everywhere. Now, in the case of periodic fields, we know that there's a neighborhood which is a group. If we restrict myself to the group, it becomes a group homomorphism. And the neighborhood is a Lie group in its own right. An open subgroup of a Lie group is a Lie group. It's a Lie group in its own right. I have a homomorphism. And take the kernel. That's a Lie group. And the kernel corresponds exactly to the Lie algebra we want. And we are done. In the real case, it becomes a little more complicated. You have this local property, and then you can extend it to a homomorphism. You cannot quite extend it into f is a homomorphism of g into k is what I've said here, of u into k, but I cannot hope to extend everywhere. What I can do, however, is go to the simply connected covering space of G. If G is a Lie group, and you take any, it's a locally connected, locally arcwise connected space, so it makes sense to talk of covering spaces. It has a universal covering, a simply connected covering, and simply connected covering inherits a group, it automatically inherits an analytic structure, because for every point you can project this, for every point there's a neighborhood which maps homeomorphically onto the image, and you can choose if you have a coordinate chart below, you get a coordinate chart upstairs. So you get coordinate charts everywhere, and it's easy to see it's a group also, universal covering, and therefore it's a Lie group in its own right. So in the universal covering, there it becomes simply connected, and once you have a mapping like this in a neighborhood with identity, you can by analytic continuation extend it to all of G. Okay? I'm working with the real or complex case now. So you get an analytic homomorphism of the universal covering, not of G, but of G tilde. Get analytic homomorphism of the universal covering G tilde into K, and then the kernel is of course the Lie group. It's a closed subgroup, and the Lie algebra is is a Lie algebra over K, and therefore you get a nice so kernel is a Lie subgroup. Now you have the natural mapping from G tilde to G, and you have this Lie subgroup kernel H contained, H tilde if you like, H tilde contained in here, and you can take the image of H tilde in G. If you choose, the point is that you can H tilde a priori is a closed subgroup, it's a Lie group, and you can take the connected component of the identity, which will have the same Lie algebra as H tilde, and take its image in G. It could, its image in G, there may be a kernel there, but you can pass the quotient by kernel. The kernel will be discrete, so the Lie algebra will not change. So H tilde modulo a discrete group will map injectively into G, and therefore you get an analytic submanifold of G. First get something in G tilde, and then you can go down to G in the obvious way. So this proves in all cases that to every subalgebra that there is a corresponding Lie subgroup. Maybe I've been a little fast here, but go and think about it. Tomorrow, if you have difficulty, to tell me, I'll go through the proof a little more carefully. In the real case, I think in the PID case, the proof is clear enough because there's a neighborhood which is a group, and then there's a group homomorphism, and you're done. But here I've said something about universal covering being a Lie group without explaining fully why, but I'll tell you that tomorrow. But today I want to continue to say something else. That's the reason I don't want to go more into it. I want to talk about differential forms, it is really does not belong to Lie theory proper, but it's more general. It's differential geometry, and it's an important thing in any case. And later on, if you want to study the topology of Lie groups, different forms are important. Differential forms are very, very much connected with topology. So M is a manifold, analytic manifold. An exterior differential P form, exterior analytic differential P form is defined as follows. It's an assignment on M. It's an assignment of an alternating multilinear P form let me give it an exterior differential form P form omega on M is an assignment of an alternating multilinear P form omega M from Tm cross Tm cross Tm to K, so P factors. It's multilinear in the sense it's, if I freeze all the other variables, it's linear in that variable. Alternating means if I switch to, sign changes. Or more generally, if I permute the vertex, it changes with signature of the permutation. So to K, such that in a coordinate chart, UF, omega takes the form sigma omega I1, I2, etc. IP dxi1 exterior, etc. dxip. It's a notation. I1 less than I2 less than IP. What do I mean by of x, M? Where omega I1, I2, IP are analytic functions. What do I mean by dxi1, etc. dxip? It's a form which takes the value dxi1, etc. dxip. I need to know it on, I need to know what it does on P vectors from a basis. Say if I look at d by dx j1, d by dx jp, what is it going to be? It's equal to 0 if I1, I2, IP is not equal to J1, J2, Jp. Equals epsilon sigma, where J1, J2, Jp, when J1, J2, Jp equals I sigma 1, I sigma 2, etc. I sigma p. Once the two are equal, they are permutations of each other. And then J1, J2, Jp is obtained from I1, I2, IP by this permutation sigma, then the value is epsilon sigma. So that's how. Huh?
The first one equal to 0. As set is not set
as sets.
the first one.
It is 0.
As a set, not the tuple. See, for example, it can be permutation of the other, right?
Yes,
That is the second case.
exactly what it is.
No, it's 0 if I1, IP is not equal to J1, J2, Jp.
Yeah.
As a set.
It may be permutation.
No, as a set, I'm not saying that it's not an ordered set.
No.
This set is not equal to that set.
Yes.
No, but usually when you write tuple, it is.
No, okay, if you like. It's a set. The two sets are not equal.
Yeah, no.
If the two sets are equal, what is the permutation that they are?
Yeah, no. Usually set.
Okay. Anyway, so if this set is not equal to that set, it is 0. If the sets are equal, then one is a permutation of the other. What by permuting the other, and I've written down what exactly it is. So that's the definition of this. And you know, these forms form a basis of the set of all multilinear alternating P forms on the tangent space at M. That's why everything can be written in this form. And all that I demand is to start with an assignment like this, and you get omega can be written like this uniquely, and this omega M have to be analytic is the demand. And once you have this, one can, so this one denotes by omega Pm, if you like, the vector space of all analytic differential exterior P forms. That's called, I write it to omega Pm. It turns out that we have a very nice natural differential operator from omega Pm to omega P plus 1m called exterior differentiation. In local coordinates, it can be written quite easily, namely d omega, if omega is this, turns out to be sigma d omega I1, I2, IP by d xk dxk exterior dxi1 etc. dxip summed over I1 I2 IP I1 is IP as well as k. Now when I write dxk, this k maybe will fit in maybe somewhere in between. I can't say that k less than I1 less than IP always, but I have to bring it to that place, which will mean a permutation, of course. So if I want to rewrite it in that form, I may have to push the xk somewhere else and modify by sign. And there may be two terms which give you the same thing, namely this dxk with dxi1 and some other dxj with dxj1 etc. dxjp may be the same up to permutation. So they will have to be combined together when you write. This is the definition of, I've written it down in one coordinate system. But if the same formula holds in any other coordinate system, otherwise it's independent. The way I've written it seems to depend on the coordinate system, but the operator does not depend on the coordinate system.
So maybe zero terms.
Sorry?
If k is one of those.
Yeah, that is zero. The point is dxi exterior dxi is taken to be 0. dxj exterior dxj. It's an alternating form. So when the two values are equal, it has to be 0. That's the understanding. The understanding is it is 0 whenever k is one of the I1 I2 IP. Next. So you have a natural map from omega pm to omega p plus 1m. And one way of writing it without the use of coordinates, one can write down the formula without using coordinates, which goes like this. You take any p plus 1 vector fields, it turns out d omega on p plus 1 vector fields hp plus 1 equals sigma xi applied to minus 1 power I xi applied to omega x1 etc. xi omitted xp plus 1 plus sigma I less than j minus 1 power I plus j omega bracket xi xj x1 etc. Omit xi omit xj. That's the formula. If x1 x2 xp plus 1 are vector fields. The remarkable thing is that d omega is really a p plus 1 form, so it depends only on the value of x1 etc. xp plus 1 at one point. Though we have written it in terms of vector fields which have to be defined in the neighborhood. But if you have a bunch of vector fields x1 xp plus 1 and another bunch y1 etc. yp plus 1 which have the same value at the point m, whether you calculate this way or that way, with the xi's or yi, you get the same answer for d omega. And this d has many interesting properties. Among other things, you have this sequence now. Start with omega 0. That this is nothing but 0 forms are nothing but functions. And then you have omega 1. This is 1 forms, 2 forms, and so on. Omega p plus 1. And you go only up to omega n because alternating forms in more than n plus variables become 0 vectors when the vector space of dimension n. We have operators d here everywhere. Turns out that d square is 0. This is the generalization of the formula you come across in vector calculus, like you know curl grad f is 0, div curl is 0. There are special cases, and there you have you're looking at differential 1 forms, different 0 forms of functions. So scalars, differential 1 forms. There are only 3. We are looking at functions values in R3, so it's a 3 variable situation. When you take vector valued functions, it's the same thing as differential forms, differential 1 forms, because differential 1 form in all of R3, it's f dx plus g dy plus h dz is what is going to look like, so f gh. And then alternate 2 forms, again it's like a vector space. It's called get only dx dy, dy dz, and dz dx. So from scalars to vectors, and again back to scalars. The first one is gradient, the second one is rotation or curl, the third one is divergence, and so on. That's the way it works. and all those compositions being 0 has the generalization to n dimensions. And it's a beautiful theorem in different geometry that if k equals R case, topology becomes interesting only in the real manifolds. For periodic manifolds, topology is uninteresting. They are all totally disconnected spaces, and every periodic manifold, in fact, is known to be a disjoint union of disks. So it's no interesting topology there. However, in the case of k equal to R, manifolds have an interesting topology, and it turns out if you look at this, since d square is 0, you can talk of the kernel modulo image, and that's called the Rham cohomology of the manifold. HP Rham MR is by definition kernel D modulo image D at the stage omega p. HP Rham MR is what I call it. It turns out that this cohomology is is isomorphic to the singular cohomology of the manifold in a natural fashion. That is known as the Rham theorem. So you have made use of all the machinery of differential manifolds and then differential structures and so on to arrive at this cohomology. Whereas in topology, you don't need all that stuff. Even for an arbitrary topological space, you can define singular cohomology. But in the case of differential manifolds, I said analytic. You can all do, in the case of real numbers, you can do it with C infinity also. And even with C infinity, the same result holds. So this is isomorphic. HP MR singular cohomology, if you like. In fact, practically any cohomology theory you can formulate for topological manifolds works. And this is known as the Rham theorem. The theorem was actually conjectured by Elie-Cartan and proved by the Rham. Well, so that's a kind of digression from the main thing, but I think it's an interesting theorem which people should know. Okay, going back to Lie groups. What I've done so far is to say that to every subalgebra there is a Lie group. But suppose you have an abstract finite dimensional Lie algebra over K. Is there a Lie group corresponding to it? That's one way. How will I, suppose I want to prove that, how will I do that? If I can make the Lie algebra, the subalgebra of a Lie algebra of a Lie group, I can apply Lie's theorem and be done with it. And what are the Lie groups you are most familiar with? GLN. So if I can find a linear representation of the Lie algebra, which is faithful, injective, then I am done. So question, does any finite dimensional Lie algebra over a field K, here it's periodic real fields, more generally I can ask over a field of characteristics 0, does it admit a faithful linear representation? The answer is yes, and the theorem due to a Japanese mathematician by name Ado. So that's a faithful representation. Theorem is due to Ado. Harishchandra gave a proof of this theorem. It's one of his early results on Lie algebras and representations, that he proved that any finite dimensional Lie algebra, by techniques different from Ado, purely algebraic, that this Lie algebra, any finite dimensional Lie algebra has a faithful representation, which implies, of course, therefore, any Lie algebra, any finite dimensional Lie algebra over K is the Lie algebra of a Lie group over K. So you have correspondence the other way around, so to speak. You can associate a Lie group even to Lie algebra, but the Lie group associated Lie algebra need not be unique. For one thing, if two Lie groups have the same isomorphic connected components, then they will have the same Lie algebra. If one is a covering with the other, then the tangent spaces are the same. For a covering space and the manifold that is covering, the tangent spaces can be identified at identity. So you will get the same Lie algebra. You won't get anything different. So it's not quite bijective correspondence, but the Lie algebra does carry plenty of information about the group. And in the O reals, to any Lie algebra, I can associate uniquely a group by first you have some group, I don't care, and then but I can take the universal covering. The universal covering is well defined. There's only one simply connected group with a given Lie algebra. Because if you have two Lie groups, two simply connected groups with the same Lie algebra, there is a mapping from between Lie algebras which will induce a mapping from the group to the group. A priori you get local mapping, but then since the group is simply connected, you get mapped the other direction. You get the mapping in the other direction as well, so the composite is an isomorphism. So to every Lie algebra, over R, there is a unique simply connected group with that as the Lie algebra. Same thing is true over complex numbers. There's no problem. Over periodics, it becomes more complicated because, for example, if you take GL and K, you can take various open subgroups. That is, take all matrices which are integral, non-singular, that is, whose inverse is also integral, and such that they are congruent to one modulo P power n, where P is the prime ideal in the local ring. I am taking integers in QP, integers in the periodic field, which will be a subring, and which has a whole lot of open subgroups, open subrings, if you like, or ideals, namely everything congruent to one modulo P power n, where P is the prime ideal there. So all of these are open subgroups. They all have the same Lie algebra. So, and so therefore, in the periodic case, there's a whole lot of others. And then, of course, you can have things with lots of connected components. So, if you impose the condition, it's in the real or complex case, if you impose the condition, it's connected and simply connected, you get a unique group. That's what happens. Now, for groups, we have notions like solubility. You know what is an abelian group. We know, I've also told you now what when an Lie algebra is abelian, when all the bracket operations are 0. If a group is abelian, the Lie algebra is necessarily abelian, and conversely. Once again, it is easy to see because, so if G is abelian, the corresponding Lie group is also abelian. Why? The point, I mean, one has to be a little careful. When I say corresponding Lie group, in the periodic case, it is a germ of a Lie group. Like, I mean, some sufficiently small open neighborhood is abelian, is all I can say. Because you can always take a small one and then make a product with some non-abelian, big non-abelian group, and you still get something which is non-abelian. Or even in, so you have to be careful about when I say the corresponding Lie group. In the periodic case. In the real case, you can always, if you assume it's connected, everything will be okay. Because you prove for the simply connected group it's abelian, then automatically all the groups are abelian. So what happens? If G is abelian, the corresponding Lie group is abelian. Why is this? You look at the group G and take its, depending on whether you are working with the periodic field or real field, you take a compact open subgroup or the universal cover, one of the two. And then you have this mapping G to R, G to K. It induces a map G to K. I won't call it a map because you'll have to make a modification. It's defined in some, defined either on open compact subgroup or on the universal cover. this will induce a homomorphism from G to K. Why is this one? The argument is you take the Lie algebra G cross K, which is the Lie algebra of G cross K, and the graph gives you a subalgebra, therefore Lie subgroup, etc. And therefore you get a morphism from G to K. And that morphism will go from G to K only if either G is simply connected or is a sufficiently small open compact subgroup in the periodic case. So you have mapping G to K. Suppose you take n linearly independent forms, you get correspondingly K cross K cross K. You get a homomorphism into this, which induces isomorphisms in the tangent space at identity. And therefore, this mapping has to be local isomorphism, which means near the identity, everything commutes, because this is abelian, this group is abelian. So near the identity, all elements commute, therefore, the group generated by that neighborhood of the identity will be abelian, which when G is connected, it's a whole group, because the group generated by a neighborhood of the identity will be an open subgroup. An open subgroup is automatically closed in a topological group, and an open and closed subgroup in a connected group has to be the whole of G. So G becomes abelian. In the periodic case, you can only say there's a neighborhood where things work, and that's fine. It maps injectively into K cross K cross K, so it's abelian. So a Lie group is abelian if and only if the corresponding Lie algebra is abelian. Now, one can see when I say Lie group is abelian, I mean either a neighborhood of the identity or the simply connected group corresponding to that. In the real case, simply connected, you don't have to say simply connected because automatically the quotients also will be abelian. Now, what happens to other concepts? The next concept, once you define abelian in the group theory, you define solubility, nilpotence, and so on. And in every case, the same kind of statement is going to be true. If the Lie group is nilpotent, if and only if the corresponding Lie algebra is nilpotent. A Lie group is soluble if and only the corresponding Lie algebra is soluble. These are things I'll prove in the next lecture. So it shows you that the Lie algebra gives you a lot of handle on the structure of a group. So what ultimately happens is this. Take any, let me say it first for reals or complex numbers. Take any Lie group or real or complex numbers. It has a maximal normal soluble subgroup such that the quotient has no abelian normal subgroups. And so basically, to study the structure, therefore, you have this maximal soluble normal subgroup, which is called the radical. Radical is built up of abelian groups, so there's hope that you can understand what happens to the radical. And then the quotient by the radical has no abelian normal subgroups whatever. Such groups are called simple groups. And a complete classification of simple groups over all these fields is now available, over the periodic fields or real fields. Periodic fields is more complicated. Over real fields, it is complicated, but much real or complex fields. It was done long ago, more than 50 years ago. The classification over periodic fields is a more recent affair, and that involves very technical things. I will not say anything about that, but I will tell you something about the classification of Lie groups and Lie algebras over real and complex fields in the next lecture. I'll stop here.